On the next Built to Last, we are continuing our look at the building envelope. Our experts in building science are back. Next on Built to Last. Hi, I'm Bruce Obora. Today we are continuing our look at the building envelope with our guest from Power Construction. Building materials are improving and the technology that makes them better is challenged by the cold and heat of our Midwestern weather. We'll put a state-of-the-art blower door to the test back at the Carpenters Training Center.
Understanding the various components of the building envelope begins here at the Carpenters Apprentice and Training Center. Instructor Craig Triplett provides a unique perspective of the techniques and materials used in attic insulation.
Now, Craig, this is a good example of what your typical attic frame will be once the house is constructed, correct?
Correct. We have basically all the ceiling joists or the bottom cords of the trusses going across our walls, interior walls. We have our ceilings drywalled. And then with the electricians making their holes through there, the plumber making their holes through the actual attic floor, our scuttle hole,
Sure.
our flues, we're going to end up with basically areas that we need to air seal.
Okay.
So once we air seal it, then we're able to add insulation. But we want to make sure it's air sealed prior to insulation. So what we have over here, we have basically an attic floor using different materials that we could possibly use. At the far end, we have cellulose that we're able to blow in once it's air sealed. We have rolls of bats, fiberglass, rolled out through the attic floor. And then we also have basically blown in fiberglass. And we have to achieve a certain R value in our attics, so in all of our buildings. So what we need to do is make sure that we use the right materials and then the right thicknesses of the materials. Again, the key is air sealing first and then the insulation.
Okay. And one of the other important factors is obviously in the attic is the airflow. So I see you have your baffles in place and things like that.
Correct, because once we get our thickness of our insulation up high enough, it'll actually block the airflow coming from our soffit
Sure.
vents. And we need to get our airflow to be able to flow up to our ridge vents so that any moisture that might be in our attic is able to evacuate. So again, no condensation issues because it's going to lead to basically rotting out our buildings.
Right. And what important too, people don't realize you have your attic access, scuttles, things like that. Everything you want to make sure you're insulating.
Correct. Most attic scuttle holes, a sheet of drywall that was cut out. They put the drywall on top of a trim package, and that's it. It needs to be gasketed. It needs to have some weight to it. So we add rigid foam to this
Sure.
to build it up, and then we add, insulation. So our scuttle hole should be, R49 if the rest of the attic is going to be R49. So we need to match the R value over that.
Okay. Again, it's just the importance of kind of carrying everything through in the continuity of really creating this whole system.
A continuous air barrier, a continuous thermal barrier.
The building envelope is the physical separator between the interior and exterior of a building. Components of the envelope are typically walls, floors, roofs, windows, skylights, and doors. A skilled carpenter has the knowledge to build an airtight envelope. Robert Falconer of Power Construction explains the importance of the building envelope to the comfort and durability of a home or commercial building.
Bad insulation, the fiberglass, the stuff that makes you itch is what most houses had in them. You put that in between the studs, and so you've got insulation in this part of the wall, but where you have the stud running from inside to outside, that's what we call a thermal bridge. It allows the transfer of that heat or cold from one side to the other.
Heat will flow in the path of least resistance. This heat transfer can occur in an uninsulated attic hatch, a single pane window, or across a wood stud in an insulated wall. Wood has a higher conductivity than insulation, so heat prefers to go through the wood from hot to cold. Likewise, metal studs in commercial construction are excellent conductors of heat. When heat takes a shortcut through highly conductive material, metal studs for example, that is a thermal bridge.
We've tried to move all of our insulation outboard where it can be continuous on the outside of the building. And that's where bad insulation is not a good product to be exposed to those types of environments. So they've come up with new plastic foams, extruded polystyrene and expanded polystyrenes, plastic insulations basically that you can run on the outside of the building that aren't as susceptible to moisture and can give you a continuous layer of insulation. And then even beyond that, now we've got spray insulations that are, again, a seamless product. You don't have bridges and gaps that you have to lap and seal. You're putting it on in a continuous application without those seams. It's a very effective and efficient product.
And even with those, just the density takes, the value is quite great for something that might be very thin.
That's correct. You know, we talk about R value for insulation. So a bad insulation is going to give you, 3 or 4 R per inch. Some of the spray foams can give you up to 6 or 7 per inch.
R value is a measure of resistance to heat flow through a given thickness of material. In theory, the higher the R value, the greater the resistance. However, it's just one key factor that determines the effectiveness of insulation material.
Can that also act as an air barrier or a vapor barrier?
Some of those can, particularly spray foam insulation, if it's applied at 1.5 inches to 2 inches, can become an air barrier. In addition to the thermal barrier, it can become a vapor barrier. So you start to get those products that you might have to use 2 or 3 products to achieve the overall desired effect now can be done with one product in some cases. So again, very efficient and effective installations.
But you should always look at what you're doing. One doesn't necessarily take the place of the other.
That's correct. And where you put it in the wall, I always use an example. I live in an old Chicago 3-flat. It's a masonry wall on the outside. From a moisture management standpoint, it's a great wall. The water moves into the brick, moves back out, and it has no place that it stops to condense. It's very fluid from that point and works very good on moisture management. But from an energy standpoint, it's a disaster. I mean, there's you're heating the outside basically. So then if you were to put a spray foam or an insulation on the inside of that brick, you could totally affect how that wall performs. Now you're stopping moisture movement. It condenses in planes that it doesn't want to, and that condensation can be problems when it's inside your building.
Back at the Carpenter's Apprentice and Training Center, carpenters are taught state-of-the-art methods to test the effectiveness of the building envelope. Craig Triplett explains the methods of testing an airtight structure.
We've gone through the various components about the building envelope, the whole construction, air sealing, insulation. Now the importance is testing.
Correct. Here we have a test mock-up house that we're going to be testing, and we basically show exactly how to run a test. And then, with this building being built the way a typical building is going to be, we've got can lights that are going to potentially have air leakage. Skylights will have air leakage locations. We've got basically a scuttle hole that has locations that might air leak. And as you see, we have windows everywhere around this building. Inside this house, we have every situation imaginable that we're able to basically test and then show where the locations are.
Okay, and so what becomes part of the test? What are the factors in this or equipment that would be used?
Well, we'd use a blower door. The blower doors are a big one. Our energy codes are requiring us to be a certain air leakage rate and under. And nowadays, with the buildings getting tighter and tighter with the energy codes, we have to verify that it's leaking. Right now, the air is leaking out of this building, but we don't know where. Sure. So what we do is something like this, where we have a blower door situated in an exterior opening, and what we're able to do is basically install it in an exterior opening. We have a fan that we're able to pressurize or depressurize the building, and then we have a calibrated manometer, another tool that's able to tell us what our air leakage rates are. This being a small house, we can use a single blower door. We can use a single fan. Larger commercial buildings, what we'll have is 3 basically fans in multiple doors, so we can create the pressure difference that's required in order to get an accurate level of air leakage, the rates that we are looking for.
Okay, and this is something that's pretty much being mandated by most municipalities and things like that for any type of new construction.
Correct. The energy codes are getting more strict, and they're mandating us test the facilities. Once we test the facilities, we have to do a simple calculation to tell us how much air is leaking out of the building or into the building, and we have to meet that in order to get basically the final approval from them to get occupancy.
And it benefits the end user. That way they know they have a building that's really performing the way it was designed to be.
Absolutely. We have a building that's going to be more energy efficient because it's not going to be leaking the conditioned air out of the envelope. They're paying to heat up the building, that heat should stay in the building. They're paying to cool down the building, that building should stay cool throughout the entire cycle, just because the air leakage is stopped and we have it thermally insulated correctly.
Okay. Now I see you pretty much have all the components in place. Is this something we can see actually activated?
Absolutely. We can run the test here and we'll show some of the tools that we use. When we have this running, again, where's the air leakage coming from? Where's the air leaking out of? We have a smoke stick that we can use. We have an infrared camera that we're able to use. The smoke stick or a theatrical smoke generator, we can actually pressurize or depressurize the building and walk around and see where the air is coming from. Our infrared camera, when I have this running, this is actually creating like a 20-mile-an-hour wind on all sides of the building. People typically know exactly where the wind is coming from. Wind's blowing from the west. They can feel it on that side of the wall. But where's it leaking out of? This shows us the entire building. And with that air, say it's colder outside, it's going to pull in that cold air. It's going to cool down our building components. Infrared camera is going to show us that by showing us where the components are colder than the rest of the area.
Okay. Now, is this something you just kind of start out? Is there a time frame for this that it has to run?
No, we basically have to calibrate it. We have it all set up, situated. We turn it on, and once we turn on the fan, we basically are going to get our numbers pretty much instantaneous.
Okay. Is this something we could get started?
Let's do it. All right, Bruce, now we have the building depressurized, and we can't see it, but we have tools such as the smoke stick, where with the smoke stick, we're able to basically kind of give it a little puff, and if there's no air movement, it's going to just kind of linger.
Sure.
But if we put it somewhere where there might be a leakage, it's going to blow it away. So if you put your hand under here, you can actually kind of feel the cold air coming in.
Right, right.
So that's what we're able to do when we depressurize the building. We're able to go around with our smoke stick or a theatrical smoke and place it in the different locations where we're going to find leakage that we may not have expected it. Another useful tool is what's called the infrared camera. So our infrared camera is basically picks up the infrared heat that we can't see. So with us depressurizing the building, it's sucking that outside air in. As long as there's a temperature difference, it's going to start heating up or cooling down our building products. So what it does is it picks up our thermal imprint of basically what's going on. I just took the my hand off that wall and it's showing up my hand. It's showing the heat that's basically resonating from our drywall.
Right.
So with our blower door running and it pulling in that exterior air, it's going to warm up or cool down our building materials. Then I'm able to go around and actually check the entire building. This is going to save a lot of time doing destructive testing on trying to find out where that air is actually leaking from.
Say, but basically you're able to pinpoint the locations rather than open a larger area that might necessarily need to be.
Correct. We're going to basically find exactly where that air is leaking from with the use of our smoke or infrared, rather than basically destroying some parts of our building to hopefully we find it, do a bunch of patches and it's destructive. Here we're able to pinpoint it a little bit better and we're able to narrow down our search. Our blower door, was going to be put on prior to the drywall being put on, the finishes. We're going to test our building to make sure that it's going to meet the requirements mandated by code. We're going to go around with our smoke and our infrared camera. We're going to find those situations. We're going to air seal it. They're going to put on their finishes so that when they come to do their final blower door test, it's going to meet the codes.
Okay, so it's a multi-step process. So it's not just something necessarily you do at the end. This is done during the phases of construction.
Correct. Once we have the finishes on there, now we're talking about destructive. And then we're going to have to really narrow it down. If I don't meet my numbers, I'm going to have to start tearing apart my building and using a lot of caulk and just trying to find little holes where I might find a big hole with my smoke or infrared camera.
Sure. But basically at the end, it's creating a tight environment and envelope for the building structure.
Right. We're making an airtight building where, again, that homeowner, that building owner is going to heat up the conditioned air inside here and it's going to stay. It's going to be a more energy efficient building for basically the end user.
And that's really what the importance is here.
Absolutely.
Okay. Appreciate the time.
I'm a quality support manager for Power Construction. I come from an architectural background, and our role at Power is to review documents and projects as they come in.
The importance of the building envelope to the overall comfort for a building begins in the design phase with architectural drawings and blueprints. Prior to the construction phase, skilled carpenters can see constructability issues before they occur on site.
We look at them for constructability issues. How is the architect shown it on paper, and can we translate that into an actual building product, or are there sequences or methods that we might suggest that would make it easier for us to construct and still achieve what the architect's goals are?
Great. So, in kind of keeping with today's conversation, we've been talking about the building envelope. And we're getting into some of the specifics. One of the things that in the market, there's a lot of different vapor barriers and air barriers, and obviously with your experience in the different types of construction, this is something you pretty much deal with regularly.
That's correct. What we've seen is a transition of materials with technology improving, things like that. We're seeing the products that are available to us both in number and sort of the technology of those products. We have to make sure that we're current with everything that's out there and how those interact with other products in the building. Tar paper used to be a way of keeping air out and controlling moisture and things like that. That's a product that comes in 3-foot rolls. So every 3 foot in your building, you've got a seam that you need to deal with, either lapping that in the right direction or dealing with that. Then they came out with building wrap products that you see very often. Those became bigger sheets and had less of these laps and conditions that you had to deal with. So that was a good thing. And now we see the technology moving into peel and stick products that stick themselves onto the building, that you don't have to put fasteners through it, holes in your system basically. And even to seamless products now, where it's either a spray applied or a roll applied product where you have no seams, so it's a continuous barrier. So as the technology changes, we get to make that performance improve in a lot of ways. And then the other component of that is these products can either be vapor permeable, which allows vapor to move in and out of it, which is a desirable thing in certain conditions, or vapor non-permeable, where it is a barrier that keeps vapor from traveling from one side of it to the other. And where you locate those in the wall is very important. We live in a climate in Chicago here that we live in primarily a warming condition. We're heating our building more than we're cooling it. So our vapor barriers and air barriers want to be placed in the wall at the proper location relative to insulation. So in our environment, we typically want that control layer to be on the warm side of our insulation. In the southern climate, where you're in cooling conditions most of the year, it's the exact opposite. You want that control layer on the outside of your insulation. So again, you need to understand where you're building and where would be the appropriate place to put some of these layers in the building.
And I assume the type of construction also has the impact, what the exterior of the building would be, as well as the functional.
That's correct. Depending on what your exterior cladding might be, you might be using one, either a permeable or a non-permeable membrane might be desirable. And those are types of things that we look at when we're reviewing the documents and making recommendations for products.
So each one kind of is really a specific application.
That's correct. Again, performance-wise, you have to understand where's the moisture trying to get from either outside into your building, or maybe you have warm, humid air in the winter that's trying to get outside. So understanding how the building's being used, what's the interior environment versus the exterior is an important part of what we look at for the overall wall construction.
Material selection plays an important role in combating the effects of thermal bridging. Once again, Steve Black of Power Construction explains a carpenter's perspective on material selection.
Steve, I appreciate you meeting with us here today. We're going to talk a little bit about the building envelope. Can you tell me about yourself and your role with construction?
Sure. I work for Power Construction. I'm a quality support manager there, and basically our role is to take the project from the very beginning all the way through the end, and we really start looking at enclosure details. That's probably the big part of our job, and then assist our project teams in any way we can to help them deliver an excellent project.
Regardless of the different systems, the enclosures, whether it's brick, siding, glass curtain wall, you take a different approach to each one, but the elements are the same to keep out.
Yeah, you're still keeping out, you're controlling air, you're controlling your thermal movements through the wall, you're controlling vapor if you need to, and you're controlling bulk water. You know, you got to keep the water out, because it's our enemy, but we can't live without it, right? It's one of those things.
Sure. And then that becomes true of any project, whether it's commercial, residential.
Correct. Yep. As long as you're not building a doghouse or a shed or something like that, if it's controlled, occupied space, you're spending money to change that environment inside, then you need to have all four of those layers continuous around the envelope.
Sure. And a lot of these projects are kind of been developed, basically, they're always improvements to
Correct.
what's on the market and what's out there.
Yeah, and I think, probably within the last 10 years and certainly within the last 20, there's been a huge evolution of products. I mean, you go back 20 years ago and everybody had, bulk water was really what everybody, I don't want my building to leak. Okay, that's fine. So we put up tar paper, which kind of controlled water, and then you clad it with some sheathing, and then, gas got expensive, so everybody said, well, let's throw some insulation in the wall, and that seemed to be working pretty well. And then, well, now we got to make it tighter, and then all of a sudden they thought they had it solved, and we ended up with a whole bunch of problems because we didn't quite understand the science of what was going on, and vapor movement and water intrusion and allowing that wall to dry at that point. And the whole idea is that whatever your envelope is, you have to assume you're going to get a little bit of water in there.
Sure.
And so how do you manage it? How does that wall have an ability to dry? So if we go back to the wall that I talked about earlier, that perfect wall, everything's on the outside.
Right.
So there's nothing, if the insulation gets wet, it doesn't care because it's designed to take it. If it's mineral wool or plastic or whatever it is, it doesn't care if it's wet or not. It may perform a little bit less if it's wet, but it really doesn't care. Everything on the inside is protected because you have that water control layer there, that membrane that's protecting it. If it's this or a peel and stick type product, where
Sure.
It's all stuck solid. If you have things inside the wall, your insulation's on the inside, it gets more challenging because then you can condense on the one side, and you just have, let's take a pool again. Everybody can relate to how humid that would be. If you have a pool environment, you have insulation in the wall, and you have a barrier on the outside, all that vapor wants to go out there and it can't get out. And then you have insulation on the inside, and now that surface is colder than it would have been if you didn't have the insulation in there.
Right.
So if I put the insulation on the outside, that's the same temperature as the room. If I move it to the inside, now it's colder, and it condenses just like it would on your soda can or beer can in the summertime. Runs down on the ground and starts rotting the framing of the wall, whatever it may be, studs, metal studs, drywall, or wood, doesn't matter.
Right,
It attacks
right.
it.
But I think the most important factor here is that the building envelope is really 6 sides.
Oh yeah, it's all 6 sides of that box. Yeah, if you want to have something that's going to perform, or high performing, right, which is what we're trying to build these days, you got to have all 4 layers on all 6 sides. Yeah, and it all needs to tie together. I think that's one of the common problems in most construction is you've got all these different elements, but they've all got to marry together. Continuity is the term that we always use, talking about an envelope integrity, right? So the air barrier and the wall has got to tie to the air control system in the window, and then back when it gets to the other side of the window. And similarly, the rain screen or cladding all has to kind of tie together, and that's got to go around all 6 sides again to keep the inside in and the outside out.
Okay. So based on that element, bringing all this together, so the assembly of the roof becomes basically you have your framing, sheathing, and then is it the same steps and elements there, water barrier, vapor barriers?
Depending on, let's take a house roof, right? I think everybody can relate to a residential roof. So usually what happens at that point is the insulation goes across the ceiling joists, right? And you have a air control layer at that point. You know, some people use, you know, again, the poly as a vapor barrier or something like that, but that also forms an air barrier. And then you tie that back to the air system in the walls. And then you've got a big open air space up above. And then you've got your sheathing and your rain shedding layers up on there, you know, shingles, metal siding, you know, whatever your roof system is, clay tile.
Sure.
So, yeah.
So the components and elements basically, you're serving the same functions.
Yep.
To mainly keep out, you know, keep out the elements and maintain an energy efficient environment.
Correct.
So.
Yep. Yeah, and it's challenging. I mean, it gets, that's what makes our day so fun, is trying to make sure all those connections get made.
Sure.
And that somebody's got them detailed right and that they get installed correctly.
Whether your construction challenge is commercial or residential structures, we hope that our guests today have helped you build a good foundation for best practices in the construction trades. I'm Bruce Obora. Thank you for watching Built to Last.
Visit the Built to Last website to learn about these topics and more.